sketch the graph for the function f of x equals x times 2x minus 20 to the 2/3 power by determining the parts a through I. F of x equals x, a polynomial term, the domain will be all real numbers, times 2x minus 20, another polynomial to a fractional exponent 2/3 power. The denominator of the fractional exponent is the root. It's an odd number here, and the domain of an odd root is all real numbers. So for part A, the domain will be all real numbers, or negative infinity to positive infinity. For part B, we want to determine whether there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. For f of x inside of the fractional exponent 2/3 power, we have an odd power of x, this is an implied first power, which will have origin or odd symmetry, subtracting a constant, which always has y-axis or even symmetry. Since the two do not match, f of x will have no symmetry. F of negative x is negative x times 2 times negative x minus 20 to the 2/3 power, which is negative x times 2 times negative x is a negative 2x, and then minus 20 to the 2/3 power. We can factor the negative out of the 2/3 power. We have a negative x. Factoring a negative out of the 2/3 power will be the third of the 2/3 is the cubed root of a negative will be negative. The 2 of the 2/3 is a power of 2 or squared. The negative square will be positive. So it will come out of the 2/3 power as a positive. Multiplying with the negative x will keep it as a negative x. A negative has been factored out, so it'll be left as 2x plus 20 to the 2/3 power. Comparing this result to the original, it is definitely not the same as the original. So f of negative x does not equal f of x, and it will not have y-axis or even symmetry. And comparing this to the original, there is a negative factored out front that doesn't exist here, but inside of the 2/3 power, the 20 is the opposite sign, whereas the 2x is not the opposite sign. So this also does not equal the negative of f of x. So it does not have origin or odd symmetry either. So for symmetry, it has none. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate 0 back into the original function, y equals f of 0, which will be 0 times 2 times 0 minus 20 to the 2/3 power, which will give us 0 times 2 times 0 is 0, and then minus 20 is a negative 20 to the 2/3 power. A negative is allowed inside of a 2/3 power because the denominator of the 2/3 power is the root, and it's an odd number, and an odd root of a negative number is just a negative number. 0 times anything will be 0, so we have a corresponding y-coordinate 0. We have an x-coordinate 0, we find a corresponding y-coordinate also of 0, and it passes through 0, 0, the origin. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, will be set to be 0. And it will be x times 2x minus 20 to the 2/3 power. Because of the x, we have x equals 0 as one of the solutions. And because of the 2x minus 20 to a power, we have 2x minus 20 equals 0 as the other solution. We can solve for x from that one by adding 20 to both sides. and then dividing both sides by a 2, which will give x equals a 10. We had a y-coordinate of 0. These are the corresponding x-coordinates, so we compare y-coordinate of 0 with them. So this will be 0, 0, and this will be 10, 0. For part E, we want to determine if there are any vertical asymptotes. F of x is a polynomial term times a positive fractional exponent. Everything's in the numerator. There is no denominator. So there will be none. For part F, we want to determine if there are any holes in the graph. F of x has no denominator, so there will be none. For part G, we want to determine the end behavior, any horizontal asymptotes or slant asymptotes. F of x is a polynomial term times a positive fractional exponent. There is no denominator, so there will be no horizontal asymptotes or slant asymptotes. But since we have a polynomial times a polynomial raised to a fractional exponent, it will have left end and right end behaviors. And since the domain has the left end as negative infinity, the right end is positive infinity, the left end and right end behaviors will be positive infinity or negative infinity. We can determine the left end behavior by taking the limit as x approaches the negative infinity, left end of the domain, of x times 2x minus 20 to the 2/3 power. Only the highest power term matters inside of the fractional exponent. That'll be the 2x. Plugging in negative infinity, 2 times negative infinity is negative infinity, raised to the 2/3 power, which means cubed root of negative infinity, which will be negative infinity, and then squared, which will be positive infinity, and then times the x, which is another negative infinity. Negative infinity times positive infinity is negative infinity. We can determine the right end behavior by taking the limit as x approaches positive infinity of the function, x times 2x minus 20 to the 2/3 power. Only the highest power term matters inside of the fractional exponent, the 2x. Plugging in positive infinity, 2 times positive infinity is positive infinity. Raised to the 2/3 power means the cubed root, which will be positive infinity, and then squared, which is still positive infinity. And then times the x, which is another positive infinity. Positive times positive is positive. Infinity times infinity is infinity, so we have positive infinity for the right end behavior. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. F of x is a product of two expressions of x, and so the derivative will require the product rule, and will take a little bit of room to work out. This can be done on another page. So f of x equals x times 2x minus 20 to the 2/3 power. For the first derivative, f prime of x, we have the derivative of the first, which will be a 1 times the second left alone. 2x minus 20 to the 2/3 power. Plus the first left alone, x times the derivative of the second, which is a power rule. Bring the power down. Leave the inside alone. Subtract 1 from the power, I will call that 3/3. And then multiply by the derivative of the inside to complete the chain rule. The first term is 1 times an expression. 1 times anything is that same thing. So we will just have a 2x minus 20 to the 2/3 power. For the second term, we can bring the constants together. We have a 2/3, we have a 2. Multiplying the numerators, 2 times 2 is 4 over the denominator 3. So it's a plus 4/3. We have an x. And then we have a 2x minus 20 to the 2 minus 3 negative 1/3 power. We want to fully factor the first derivative. There is a common factor of a power of 2x minus 20. We can factor out the lower power of the 2. That'll be the negative 1/3. It's lower by being negative. So 2x minus 20 to the negative 1/3 power can factor out. Factoring is division, and division is subtraction of exponents. By factoring out a negative 1/3 power, we will be subtracting a negative 1/3, which is equivalent to adding a 1/3 power to each. So for this first one, 2/3 plus 1/3 will be 3/3 or 1. It'll become a power of 1, which is just 2x minus 20. Adding a 1/3 to this one, negative 1/3 plus 1/3 is 0, and anything raised to the 0 is a 1. So we have 2x minus 20 plus 4/3 x left over. We'll leave the 2x minus 20 to the negative 1/3 power alone. We want to combine like terms together inside of the square brackets. There are two x terms. We need a common denominator, so we're going to multiply the 2 by 3/3. It'll be 6/3 x. We will also want to get a common denominator with the 20 so that we can factor the denominator out. The 20 times 3/3 will be 60/3 with the negative. And we have plus a 4/3x. So we have a 2x minus 20 to the negative 1/3 that we'll leave alone. Combining like terms in the square brackets, we'll turn into parentheses now. 6/3x plus 4/3x will be 6 plus 4, 10/3x. And we have a minus 60/3. There is a common factor of 10 in the numerator and 3 in the denominator inside the second expression. We can factor out a 10 in the numerator and a 3 in the denominator. We'll move to the front of everything. And we have a 2x minus 20 to the negative 1/3 power. And factoring that out, we'll leave behind a 1x minus 60 divided by 10 is 6. And we factor out the common denominator of 3, so x minus 6 is left over. We want all powers to be positive, so we will move that negative power to the denominator to become a positive power. The 10 stays in the numerator. The x minus 6 stays in the numerator. There's a 3 in the denominator. And the 2x minus 20 will move to the denominator to become a positive 1/3 power. That 1/3 power can be written as cubed root. So it'll be 3 times, and then the cubed root of 2x minus 20. Since it's an odd root, we will want to fully factor that as well. There's a common factor of 2 in there, because odd roots can be positive or negative. It's best to have them fully factored. There's a common factor of 2. It cannot come out of the cubed root, since it's not a perfect cube. But it'll leave behind an x minus 10. there's the version of the first derivative we're going to want. So that was 10 times x minus 6, and then divided by 3 times the cubed root of 2 times x minus 10. So we have the first derivative written as a single fraction, all powers are positive, and it is fully factored. So we can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, already being factored, the x minus 6 factor will give us x equals positive 6. From the denominator, it's also fully factored. The x minus 10 factor will give us x equals positive 10. We'll now check to see which of these are in the domain. The domain is all real numbers. X equals 6 and x equals 10 are both real numbers. They are both in the domain. They are both critical numbers. We can now draw a domain line. It has no left end because it begins at negative infinity, and it has no right end because it ends at positive infinity. We can put all critical numbers on here in order. 6 comes before 10. This splits the domain interval into 3 separate intervals. We can pick a test value in each of these intervals. The first interval, negative infinity up to 6, we can pick 0. Between 6 and 10, we can pick 8. And 10 to positive infinity, we can pick 20. We can test the trend in each of these intervals by plugging the test values into the first derivative. We only care whether it is positive or negative. So the best place to plug in is the fully factored version. That's this one here. For this, the 10 is always positive and the 3 is always positive, so they do not affect whether the first derivative is positive or negative, so we can ignore those and just plug into this portion of it. Starting with the test value of 0, 0 minus 6 is a negative over 0 minus 10 is a negative times a 2 is still a negative, and the cubed root of a negative is a negative. We have a negative over a negative, which is a positive, and the positive first derivative corresponds to an increasing trend. Plugging in the test value of 8 into the portion of the first derivative that matters, 8 minus 6 is a positive, over 8 minus 10 is a negative, times 2 is still a negative, and the cubed root of a negative is a negative. We have a positive over a negative, which is a negative first derivative, which corresponds to a decreasing trend. Plugging in the test value of 20 into the portion of the first derivative that matters, 20 minus 6 is positive, over 20 minus 10 is positive, times 2 is positive, the cubed root of a positive is a positive. We have a positive over a positive, which is a positive first derivative, and this corresponds to an increasing trend. Right at the critical number of x equals positive 6, we have the trend changing from increasing to decreasing. So x equals 6 will be a relative maximum. X equals 6 came from the numerator, so it will be a normal relative maximum. It has an x-coordinate of 6 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. Y equals f of 6, which is going to be 6 times 2 times 6 minus 20 to the 2/3 power, which is 6 times 2 times 6 is 12, and then minus 20 to the 2/3 power, which which is 6 times 12 minus 20 is negative 8 to the 2/3 power. So it'll be 6 times 2/3 means the cubed root of negative 8. Now the cubed root of a negative is negative, and the cubed root of 8 is a 2. So negative 2, and then to the power of 2. A negative squared is a positive, and 2 squared is a 4. 6 times 4 is a 24. So it has a corresponding y-coordinate of 24. Right at the x-coordinate and critical value of 10, we have the trend changing from decreasing to increasing. That makes x equals 10 be a relative minimum. X equals 10 came from the denominator, and therefore it's not a normal relative minimum, it will be a relative cusp minimum. It has an x-coordinate of 10. It has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 10, which is 10 times 2 times 10 minus 20 to the 2/3 power, which is 10 times 20 minus 20 to the 2/3 power. And 20 minus 20 is a 0. 0 raised to any non-zero positive power is a 0, and 10 times 0 is a 0. So you have a corresponding y-coordinate of 0. No surprise there, because we had found that as one of the x-intercepts up above. For part I, we want to determine the intervals of concavity and any inflection points. All of this involves the second derivative. We will take the second derivative from the first derivative. We do not want to use the fully factored, simplified version of f prime of x. And we will need a little bit of room to work this out on the other page. F double prime of x equals. The best one to use for the second derivative will be this version of the first derivative, because it is a product rule. This one can also be used as well. Either way, it is a product rule. The 10/3 will come along with it. So we have the 10/3. We have the derivative of the first, which is a power rule. Bring the power down, negative 1/3. Leave the inside alone, 2x minus 20. Subtract 1 from the power, I will call that 3/3, and then multiply by the derivative of the inside to complete the chain rule. Times the second left alone, plus the first left alone, the 10/3 comes along, 2x minus 20 to the negative 1/3, all left alone, and then times the derivative of the second, which is just a 1. For the first term, we can bring all the constants together. There's a 10/3, a negative 1/3, and a 2. Multiplying all the numerators, 10 times negative 1 is negative 10, times the 2 is negative 20. Over multiplying the denominators, 3 times 3 is a 9. So negative 20 over 9. There is an x minus 6. And there is a 2x minus 20 to the negative 1 minus 3, negative 4/3 power. For the second term, we can bring the constants together. There is a 10/3 and a 1. 10 thirds times 1 is 10 thirds. And there is a 2x minus 20 to the negative 1/3 power. We want to fully factor the second derivative. There is coefficients that can be factored. There's a 20 over 9 and there's a 10 over 3. It's best to have a common denominator between those before we factor out. So we will multiply the 10 over 3 by 3 over 3. So we have a negative 20 over 9, x minus 6, and 2x minus 20 to the negative 4/3 power, plus multiplying by 3 over 3 will give 30 over 9. This makes it easier to factor out from the denominator. We can factor a 9 out from the denominator. And then the 2x minus 20 to the negative 1/3 power. So we can factor out common factors here. From the numerators, we have a 20 and a 30. They have a common factor of a 10. The denominators are both 9, so we can factor out a 9 in the denominator. And we can factor out a power of 2x minus 20 from each, the lower power of the two. And that'll be the negative 4/3. It's lower by being more negative. So we can factor out a 2x minus 20 to the negative 4/3 power. Factoring out the 10 over 9, the 10 from the numerator will leave a 2 here and a 3 here, and the 9 from the denominator will just take the denominators away. Factoring out the negative 4/3 power, factoring is division and division is subtraction of exponents, we will be subtracting a negative 4/3 power, which is equivalent to adding a 4/3 power to each. Adding a 4/3 to this one, negative 4/3 plus 4/3 is 0. It will become a power of 0, and anything raised to 0 is a 1. There's what's left over for the first term. It'll be a negative 2 times the quantity of x minus 6. For the second term, adding a 4/3 power to that, negative 1/3 plus 4/3 is 3/3, or 1, and all this will be to the first power. And we have left a 3 times 2x minus 20 for the second term. So we have left after factoring a negative 2 times an x minus 6 and a plus 3 times 2x minus 20. So we have a 10 over 9, a 2x minus 20 to the negative 4/3 power. And inside the square brackets, we can distribute the negative 2 in here, which will be negative 2x plus 12. And we can distribute the positive 3 in here, which will be plus 6x minus 60. So we have a 10 over 9 that we will leave alone, a 2x minus 20 to the negative 4/3 that we will leave alone. We can combine like terms together inside the square brackets and turn them into parentheses. A negative 2x plus a 6x will be a 4x, and a positive 12 and a negative 60 will be a negative 48. We want all powers to be positive, so we can move the 2x minus 20 to the denominator to become a positive 4/3 power. The 10 will stay in the numerator. The 4x minus 48 will stay in the numerator. There is a 9 in the denominator, and the 2x minus 20 will move to the denominator to become a positive 4/3 power. We want to fully factor the second derivative. In the numerator, there is a common factor of 4, and that will multiply with the 10 to become 40. Factoring a 4 out will leave behind an x and a minus 12. In the denominator, we can factor a 2 out inside of the 4/3 power. 2 is not a perfect cube, so it'll stay inside of the 4/3 power, which means cubed root in 4th power. Factoring out leaves behind an x minus 10. All of that will be to the 4/3 power. There's the version of the second derivative we're going to want. So we found the second derivative to be equal to 40 times x minus 12 divided by 9 times 2 times x minus 10, and that entire quantity to the 4/3 power. So we have the second derivative written as a single fraction. All powers are positive. It is fully factored. We can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. From the numerator, since it's factored, the x minus 12 factor will give x equals positive 12. From the denominator, the x minus 10 factor will give us x equals positive 10. We now check to see which of these are in the domain. The domain is all real numbers. X equals 12 and x equals 10 are both real numbers. They are in the domain, and they are both candidate numbers. We can now draw a domain line, a line representing the domain. It has no left end because it starts at negative infinity, and no right end because it ends at positive infinity. We can put each of the candidate numbers on here in order. 10 comes before 12. This splits the domain interval into 3 separate intervals. We can pick a test value in each interval. The first interval, negative infinity to 10, we can pick 0. The interval 10 to 12, we can pick 11. And then 12 to positive infinity, we can pick positive 20. And we can test the concavity by plugging these test values back into the second derivative. We only care whether it is positive or negative, so we'll plug into the fully factored version, which is this one here. A couple things about this. The 40 and the 9 are both positive, so they will not affect whether the second derivative is positive or negative. But also, this entire expression to the 4/3 power, which means cubed root, but then to the 4th power, which is an even power and will always be a positive, also will not affect whether the second derivative is positive or negative. So the only portion that does matter is the x minus 12. So we'll plug our test values into x minus 12. For the first test value, 0. 0 minus 12 is a negative. We have a negative second derivative. This corresponds to concave down. Plug in the test value of 11 into the portion of the second derivative that matters. 11 minus 12 is negative. We have a negative second derivative, corresponds to concave down. And plugging the test value of 20 in to the portion of the second derivative that matters, 20 minus 12 is a positive. We have a positive second derivative, which corresponds to concave up. Right at the candidate number of x equals 10, we have the concavity not changing. It's concave down and then concave down again. That's not a surprise because x equals 10 from over here was a relative cusp minimum, and cusps will show up in the second derivative as well, but the concavity will not change. So that checks out, and that corresponds to the cusp minimum. Right at the candidate number of x equals 12, we have the concavity changing from concave down to concave up. So x equals 12 will be an inflection point. It has an x-coordinate of 12 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 12, which is 12 times 2 times 12 minus 20, and that entire thing to the 2/3 power. This is 12 times 2 times 12 is a 24, and then minus the 20 to the 2/3 power. 24 minus 20 is 4 to the 2/3 power. So we have a 12 times a 4 to the 2/3 power. Four is not a perfect cube, so we have to leave it to the 2/3 power. We can square it and call it 16, and it is also equivalent to the cube root of 16. But 16 is not a perfect cube and doesn't simplify much from there, so we can leave it just as 4 to the 2/3 power. We can now draw a graph of the function. We have a vertical axis. We have a horizontal axis. The domain is all real numbers, so all x values will be represented here. There is no symmetry. We do have a y-intercept at the origin 0, 0. We can label that. We have an x-intercept also at the origin. No surprise there, it's crossing both axes at the origin. And we have one at 10, 0, which will be over here. And we can label that. We have no vertical asymptotes, no holes. We have a left-end behavior of negative infinity, which means on the left end it'll end up down here somewhere. And right-end behavior of positive infinity, so on the right end it'll end up here somewhere. We'll be sure that it follows that. Right at the point 6, 24, we have a relative maximum. So that'll be up here. We can label it 6, 24, and it'll take a relative maximum type of shape. It's a normal relative maximum. So it'll look something like so. Right at the point of 10, 0, we have a relative cusp minimum. That's here. It's one of our x-intercepts. It's going to take a cusp minimum shape, which cusps have a vertical tangent line, so they're vertical and they look something like that. And right at 12 comma 12 times 4 to the 2/3 power. Now 4 to the 2/3 power is going to be bigger than 4 to the 1/2 power. 2/3 is bigger than 1/2. 4 to the 1/2, which is the square root of 4, is a 2, and 12 times 2 is a 24. It's going to be higher than 24. So it's going to have a higher y-coordinate than 24, which just means it's going to be higher than this point here that we found to be a relative maximum. So it'll be a little bit higher there. Something like here. And we can label this point as 12 comma 12 times 4 to the 2/3 power. And it's going to have a shape of being concave down on the left and concave up on the right. And now we can connect the pieces together. It's going to be concave down and increasing for everything over here. So it's going to take a shape passing through here of concave down. So it's curving downward, but it's headed upward by increasing. It continues to be concave down, but now it's decreasing in here. So that'll be like so. It's still concave down, but it's increasing on the right side of the cost minimum until we reach the inflection point, at which point it's going to change over to being concave up and increasing right at this point here. It does have a domain of all real numbers. It covers every x value. And it does have the left-end behavior of negative infinity and the right-end behavior up here of positive infinity. So it's checking out on all conditions there. So this will be the graph of f of x.